Hello students, welcome to the course on solutions. So in previous video, we discussed about the ideal solutions and non-ideal solutions. Ideal solutions are the solutions which obeys Raoult's law over an entire range of concentration. And non-ideal solutions are the solutions which does not obey Raoult's law over the entire range of concentration. And in non-ideal solutions, they will show two types of deviations. One is positive deviation and another one is negative deviation. So what are the differences between the solutions which shows positive deviations and the negative deviations from Raoult's law? Now, in today's lecture, we are going to discuss about another kind of solutions. Those are known as azeotropes, or they are also known as azeotropic mixtures. So azeotropes, these are the solutions or binary mixtures which will boil at a constant temperature having the constant proportion. Their composition is same and boils at constant temperature. For example, if I consider 95% of ethanol by volume, that is 95. If I consider 100 ml of this solution, 95 ml of ethanol and 5 ml of water will be present in this kind of mixture. So this is an example of azeotropic mixture. So here what happens means, when distillate the mixture of ethanol and water, then upon heating the vapors of ethanol and water will be formed, and when it is subjected to fractional distillation, we will get the mixture where it consists of 95% of ethanol by volume. So here we can't get the 100% pure ethanol. This 95% ethanol by volume, it is also known as rectified spirit. Rectified spirit. So where the solutions where we cannot able to separate completely the two components from the solutions are considered as azeotropes, or it is also defined as the binary mixtures having constant proportions and boils at a constant temperature are considered as azeotropic mixtures. In azeotropic mixture, there are two types. The first type of azeotropic mixture is minimum boiling azeotrope. Minimum boiling azeotrope. And the second one is maximum boiling azeotrope. So these are the two types of azeotropic mixtures. Then first we will see what is minimum boiling azeotrope. Minimum boiling azeotropes are the azeotropic mixtures which shows the large positive deviation from Raoult's law. The solutions which shows large positive deviations from Raoult's law are said to be minimum boiling azeotropes. And the example of minimum boiling azeotropes is the mixture of ethanol and water. Ethanol and water. Okay. The second one is maximum boiling azeotrope. The maximum boiling azeotropes are the solutions which shows the large negative deviation from Raoult's law. An example for this type of azeotrope is the mixture of water and nitric acid. Water and nitric acid, where 68% of nitric acid and 32% of water is present in the given mixture. Above that, we cannot separate the further HNO3 and H2O. So, when this composition has been reached, then the mixture will start to boil at a constant temperature. Both H2O and HNO3, they will start to boil at a constant temperature. Since the boiling point of water is 100 degrees Celsius. But also, when they are combined with each other, the boiling point of the water and HNO3 becomes 395.1 Kelvin. That is obviously greater than 100 degrees Celsius. Okay, or 373.15 Kelvin. So here the boiling point of the solution increases. So they will boil at maximum temperature and hence they are considered as maximum boiling azeotropes. In the case of minimum boiling azeotropes, the mixture of ethanol and water, 95% of ethanol and 5% of water is present. And here the water boiling point is 100 degrees Celsius. But when they are mixed with each other, the boiling point will decreases to nearly 78 degrees Celsius. And hence the mixture will boil at minimum temperature and hence they are said to be minimum boiling azeotropes. In minimum boiling azeotropes, their boiling point decreases, and in maximum boiling azeotropes, their boiling point increases. Means the solution will boil at maximum temperature, and in minimum boiling azeotropes, the solution will boil at maximum temperature. Minimum temperature. Okay, so these are the two types of azeotropic mixtures and examples for those azeotropic mixtures. Now the next topic in the solution is colligative properties. So what does this colligative properties means? The properties which mainly depends upon the number of solute particles irrespective of nature of solute and solvent are said to be colligative properties. And some of the colligative properties are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. These are the some colligative properties. And these all properties are dependent on only the number of solute particles which are present in the solution. So we will study one by one of these colligative properties. The first colligative property is relative lowering of vapor pressure. So as you all know, when the solid solute is added to the solvent, the boiling point of the solvent increases and vapor pressure of the solvent decreases. So vapor pressure of the solvent upon addition of non-volatile solute decreases, and that is simply known as lowering of vapor pressure. Okay. Now, how the lowering of vapor pressure and mole fraction are related to each other? That is given by relative lowering of vapor pressure. And for that we will derive an equation, and first we will consider the Raoult's law. And according to Raoult's law, the vapor pressure of a solvent, if I consider that one as P1, the vapor pressure of a solvent is equal to the vapor pressure of pure solvent, that is P1 naught into X1, that is mole fraction of that solute present in the solution. So P1 is equal to P1 naught into X1. Now this is the mathematical expression for Raoult's law, and as you know, when we add a non-volatile solute, suppose I have taken a solvent, the pure solvent. Now in this solvent I will add a non-volatile solute. Upon addition of a solute to this solvent, the vapor pressure of this solvent gets decreases. Okay, the solvent vapor pressure gets lowered by addition of non-volatile solute. Now they have to change in. Suppose if the initial pure solvent, its vapor pressure is P1 naught, and the solute, after addition of solute, it will form a solution, and the vapor pressure after addition of the solute will becomes P1. If I want to calculate what is the change in the vapor pressure, then it is represented as delta P1 is equal to what? The vapor pressure of solvent, that is P1 naught, minus vapor pressure of the solution, that is P1. So by taking the difference between vapor pressure of the solvent, pure solvent, and vapor pressure of the solution, we will get the change in vapor pressure, okay, after the addition of non-volatile solute. How much vapor pressure has been changed with the addition of this non-volatile solute can be calculated by using this formula. Okay, now here I will simply substitute some values. Okay, delta P1 is equal to P1 naught minus P1. What that P1 means? See this equation. If I consider this one as equation 1, from equation 1, what you will get? P1 is nothing but what? P1 is equal to P1 naught into X1. So substitute the value of P1 in this second equation. Call this as equation 2. So substituting the value of P1 in second equation, what I will get? P1 naught into X1. Because P1 is equal to P1 naught into X1. Now simplify it. Delta P1 is equal to, what is the common here? P1 naught. What will remain here? 1 minus X1. So that is delta P1 is equal to P1 naught into 1 minus X1. And what this 1 minus X1 represents? As you know, mole fraction, it is for binary solution, it will be X1 plus X2 is equal to 1. Okay, the sum of the mole fraction of the components is always equal to 1. You know this relation. So if I bring this X1 at the right hand side, the X2 is equal to 1 minus X1. It becomes X2 is equal to 1 minus X1. So substitute, instead of 1 minus X1, substitute the X2. So this can be written as P1 naught into X2. So delta P1 is equal to P1 naught into X2. So now delta P1 divided by P1 naught is equal to X2. I have rearranged this equation. I will get delta P1 divided by P1 naught is equal to X2. And delta P1 means what? P1 naught minus P1. Here equation 2. Delta P1 is equal to P1 naught minus P1. Okay, substitute that value and divided by P1 naught. This I will get is equal to What is equal to X2. What is X2? The mole fraction of solute. X is nothing but mole fraction and X2 means mole fraction of solute. And now P1 naught minus P1 divided by P1 naught is equal to mole fraction of solute, that is X2. I have already, it is written here X2. How you will find the mole fraction of X2? It is simply N2 divided by N1 plus N2. N2 means number of moles of solute divided by number of moles of solvent plus number of moles of solute. Then I will get the mole fraction of that solute. And if the solution is very dilute, then the number of moles of solute is very less as compared to number of moles of solvent. Hence, I will neglect this N2. Then what I will get? P1 naught minus P1 divided by P1 naught is equal to N2 divided by N1. Okay, this is the another form of relative lowering of vapor pressure. So remember this P1 naught minus P1 divided by P1 naught. This left hand side, this indicates the relative lowering of vapor pressure. Now you can see here P1 naught minus P1 divided by P1 naught is equal to, how you will find the number of moles of solute? N2. You know the formula. N is equal to W divided by capital M. W means given mass divided by molar mass of that component gives the number of moles. Okay, so N2 here not, here N is there, here N2 is present. So N2 is equal to given mass of solute divided by molar mass of solute. Okay, and N1 means that can be determined by W1 divided by M1. Given mass of solvent divided by molecular mass of solvent. So substitute the value of N2 and N1 in this equation. What I will get? N2 in place of N2, substitute W2 divided by M2 whole divided by N1 means W1 divided by capital M1. So rearranging this, what I will get? P1 naught minus P1 is equal to P1 naught is equal to W2 into M1 whole divided by W1 into M2. So this equation is used to find the relative lowering of vapor pressure as well as molar mass of solute, molar mass of solvent, given mass of solute and given mass of solvent. So this is the relative lowering of equation for relative lowering of vapor pressure. See here, once again I have written the formula of relative lowering of vapor pressure. So here in this equation, P1 naught is vapor pressure of P1 solvent, P1 is vapor pressure of solution, that means after addition of solute, what will be the vapor pressure, and then W1 is mass of solvent, given mass of the solvent, M1 molar mass of the solvent, W2 mass of solute, and M2 molar mass of solute. Okay, so remember this equation for relative lowering of vapor pressure and the terms which are included in this equation. So based on this, we will solve problems in next video.